Okay, good. Well, we're not doing a demo today, so we got all the technical difficulties out at the beginning. My name is Ranbir Chawla. I'm the VP of Engineering at AudienceScience.
Yeah, I'm Frank Conrad. I'm the Chief Architect of AudienceScience.
And a little bit of background on AudienceScience. We're a fully integrated end-to-end advertising solution for some of the world's largest digital advertisers. We process and respond to 80 billion advertising requests a day. And we do this in over 42 countries worldwide, including China. Our solution allows advertisers to effectively manage and leverage their consumer data to produce industry-leading ROI. We have 5 points of presence, 2 in the United States, 1 in Europe, 2 in APAC.
Yeah.
And what we wanted to talk to you a little bit about today was just the challenges of doing what we do at such a large scale. I'll hand it over to Frank.
Yeah, and basically we started 2014 with 20 billion, right now 80 billion, so it's a lot growing forward, and we had a lot of challenges with that. And it's really about the details. If you look to a Formula One car, every screw matters. If you do the wrong stuff in, the engine will die or something like that. And it's really the things about that every step must be working, and you are at the starting time always looks to the complex problem, to the heavy things, what you have to do, but the things what will kill you probably are the more trivial stuff, more basic stuff, or things which you start thinking about too late. And sorry. The things, what I really want to say, you have to start with the right data model. The things what you do, you have to think about the scale you need. Does your data model allow the sufficient parallelism to do this? Store your data in a way that you can effectively use it. Many times you start store the data in a simple way, but then the usage gets very, very expensive, and you have a lot of problems with that. And another thing what you really need to care about is your outliers. So the standard stuff, typically you get relatively good done. What you kill you is the outliers. Users which have 10,000 impressions for whatever reasons, or your data records get huge for only a couple of users. But this big users basically kill your process because it needs too much memory, and then your JVM dies, or you have a stream processing, and certain users take too much CPU times, and because of the synchronization what you internally have, it delays everything. So such a thing is really the stuff at productions what you need to care about. And then also how to design things, think about how you add things on top of it, because requirements from production, from a product will come, put more and more stuff on it. And if you not think a little bit ahead, you get at that scale really, really problems. And then what many guys also forget, it's easy to create data, or it's a challenge to create data, but it's a much bigger challenge to delete and expire data. So a lot of databases, what you have, for example, user-oriented stuff and so on, if you do data expiring not by design in a good way, you will really suffer. This cleanup jobs which runs over your database will kill your performance. So basically, this is a very big learning that in any data storage what you design, don't forget about deletion of data. If you not have naturally time-oriented data, then it's easy. But everything which is user-oriented or campaign-oriented or whatever other, which don't have a real time component in it, it gets problematic. And also, the important thing is, one, on scale. As I said before, you have to have the right parallelism, otherwise you will not get the amount of performance. You need about dynamic parallelism. Think about dynamic parallelism. What I mean with that is that you can scale up and scale down your runtime to the need what you have, especially if you leverage the cloud or something like this. You can start more servers to your rush hour and lower this down later again. But if you don't have it designed into your system, it will not work and you can't really leverage it. Think about really do asynchronous processing for everything what you could, where it is possible. What you don't have to do in your real-time response, for example, to a bit request or to a request which comes from the user browser, don't do it. Do it later. Then really look to the needed latency and throughput, because you can design systems with a low latency and don't have a high throughput and vice versa. So you have to find your needed compromise for that. Then another thing really which you need to think about is eventual consistency. This concept can help you a lot in a huge distributed way. We have, as we said, we have 5 data centers in the world where we receive all the bit requests and user requests. And if you want to have some consistency, this is something which produces huge effort and has not so much value. If you think about a little bit more eventual consistency, you can solve a lot of problems with much less resources. Then the other piece in your design is really think about production-oriented. This means have some dynamic limiting. So if you get more traffic, or if your new code release has some problems, or other things, that you have a chance to limit the incoming requests, do some throttling, do some no operations on 10% of the requests is better than do nothing, because your complete system get overloaded and do nothing then anymore. So basically that is a big thing which helps you to survive in certain situations. Think about how you can do good catch up. So if you have a stream processing and it goes behind because of performance problems, of hardware issues, or whatever, that you have ways of efficient catch-up processing, which needs you need to care about. It's also how to handle unreliable networks. So if you transfer data from one data center to the other, you will have sometimes a problem that your network doesn't work as your local network at home in a good way, that you have packet loss, that you get unexpected latency things, and so on. How you mitigate them into production. Everything in your test environment will always work well because you don't have then typically network problems. The network problems comes in the real world. And especially if you have to go to China and have the great firewall between that is really something which can cause any possible network issue what you can think about. And there will be happened because of Murphy. And this is basically also the next piece in another direction of your hardware, your servers. Think about that you have not equal servers. You have some which have 24 cores, the others have 32 cores. They have a little bit more memory, they're slightly different CPU performance characteristics, that your system still can completely leverage them, and not the slowest server in your cluster dictate the overall performance of the system. easily to achieve such things if you not look to. Then, as I said before, it's really the things about the outlayers in terms of compute power, what you need for the certain requests, memory things, and also lookup time into databases or stores, what you have to do. And the really most important stuff for production-oriented is monitor, monitor, monitor. Design in your application that you can monitor all the critical values, have them available to Grafana or something like this, as well as you can leverage to a monitoring system like Nagios, where you can check certain thresholds and do alerting to it. That is really something what I can must recommend, and typically in the development is forget. The developers forget about monitoring. But if you don't do it right, you fly blind. And the things, what we do in monitoring is we use a simple tool called Nagios for that. It's well known. And the reason why we use it is it's easy to script, and it's easy to version controlled. Because if you go in a larger deployment where you have a lot of servers, a lot of service instances, which you need to check, and you have to check every instance, not a general, one general to the load balancer. You have to check every bidder behind the load balancer that they're behaving as you expected. Because Murphy said that one JVM or one server get a problem, and not all at the same time. And that you can achieve this also on a larger scale is really neat, that the configuration is done in a completely automated way, also part of your you have to see it as a part of your deployment, of your total stuff. And as I said, bad hardware can really result that your workflows in a cluster or your bidder response time get really bad. And partners like Google, they're looking to the 95% percentile of response time. And if you are not good in that, they will throttle you. And another big part on it is basically the functional monitoring. So many times guys using check proc and see there's a process which does its job, so everything is fine. This is something which is typically by far not sufficient. You should really implement functional checks, implement a kind of end-to-end monitoring, that you simulate something at the front end and basically looking on every step on the whole chain until reporting everything that this data is showing up. Because with that, you can make sure that your whole pipeline is working. And you have to do this really on every instance. Because if one bidder or one ad server doesn't forward their data records to the reporting system, you have some number discrepancies. And you can only figure that out if you have a check against each instance of your software, what you are running. And with end-to-end monitoring, you will see a lot of more problems earlier as the customer see it. If you make it properly, you know the problems before the customer. Okay, now we go a little bit to the Hadoop stuff. As we said, we process a huge amount of data, and how to do it right now, or how we do it right now, is really mainly map-reduced jobs, which we are running to processes. We have started a couple of years ago with 60 nodes. Right now, we are more than 500 nodes. We are running them right now based on the Cloudera infrastructure. And the thing is, the pieces what we are learned there is really do as much as possible in the mapper phase from the work, minimize the shuffle data. Even if you have a very good network, 10 gigabit shuffling is this stuff where MapReduce can easily get inefficient. And this is one of the things why Spark in many times can be more efficient, because they do a clever way, a better way in shuffling data around. Then another big piece is the output of the jobs must be in a format and in a way that's also optimal for the next inputs. So it doesn't fit that your actual job running well and produce a huge amount of small output files, which end up that the next job who's consuming this get a lot of mappers, and you get there the inefficiencies. And if you get more and more nodes, many guys say, oh, have one big cluster, then everything runs faster, and we run everything on one cluster. It's theoretically a good thing. In a practice, it's not so good, because if this cluster get, for whatever reasons, a problem, you don't have any cluster. Also, if you want to upgrade things, can you upgrade your whole software at one point? Typically not. Typically, you have a migration process. If you have the stuff already split it across multiple clusters, it helps you to do this operational things in a much easier way. What you should care about is that you can relatively easily move a node from one cluster into the other. Things that the networking is in this way transparent to do such things. As I said, the optimization on the jobs itself is the runtime of each task should be in a reason of a couple of minutes. Five minutes is a good optimum. The number of mappers and reducers must be really under the consideration is how much shuffle you need. Does this get into a problem? Then you have to do their redesign stuff, as well as the size and the amount of output files. Then another thing, what you sometimes will see on the cluster, that get a huge load. That the load on the servers goes to 100 or even higher. This is a good indicator that you have a GC problem. That as your GC runs crazy, and this is one thing what is relatively difficult to monitor on the Hadoop clusters. That the GC is a problem, and it will have a huge effect to the total runtime of your tasks. Typically, you should really enable speculative task execution. This will help you, especially on hardware problems, a lot to make the things, but not on S3 writes. There you get a huge problem to do this. Then another important learning is create file system instance for every input and output what you do separately. Otherwise, you are limited to one kind of file system. So if you run in Amazon or Google Cloud and have some on HDFS, some on the object store, you need to have this separated. Otherwise, you get a huge amount of error messages and your job don't run. Good. Now,
and talk a little bit also about how we use Storm. We use Storm to do a lot of our real-time processing for user segmentation, so user information will come in, and we still stream directly from Kafka to Storm into Cassandra and into Hadoop. And we found a couple of things, that we've learned over time, right? Really only group things if you need to within the Storm topology, right? If your processing time for if your streams and the processing time have a large distribution, so some pieces that you're going to go for. So if in your topology or if in your streaming, you go out to an external system to gather information about a step within that stream, and you can have a large distribution of response time, right? That will slow your whole topology down. So if you're going to get external data, look for an in-memory data store like Voldemort, something that you can quickly get with a normalized response time that you can kind of count on within a very short window of time. Also, minimize, again, shuffling, right? This is the same problem whether you're in Spark, Cassandra, Hadoop, Storm, any of these things, right? Keep the data where the data is to the absolute maximum that you can. And same message all the time, right? It's a Java-based process. Don't create any extra garbage that you don't need. Think it through a lot, right? When you get to this massive amount of scale, the less you can create, the absolute better, right? There's no amount of GC tuning that makes up for 80 billion of these a day if you're being sloppy. And it's just it's the little things in here that make all the difference. So as I mentioned, we use Voldemort as a large-scale key store, right? We use both in-memory Voldemort, and we also use the read-only stores, right? The in-memory Voldemort is very stable. It scales well. It's really performant. But it's really hard to monitor what's in memory, right? So you have to be careful. Make sure that the input is quality, because if you don't have quality input, it's hard to go back and debug data that you're getting out of that data store later. The read-only stores, the file-based read-only stores are extremely efficient. We can produce some of MapReduce very quickly and swap those in. It scales well. It's very performant. It's very, very stable. We use the newest Voldemort client, which is handles failure and edge cases a lot better. Earlier versions we've had issues with in the past. One of our challenges has been how to swap in the data from the big read-only stores, right? How to move a tremendous amount of data into a read-only store versus what was previously there. We've done it a number of different ways. Just to let you know, one of the things we're trying now is we're moving some of these to the cloud to an Amazon environment is literally using block storage in Amazon and loading an EBS volume with the new data store, right? And basically unmounting the old one, mounting the new one, restarting Voldemort, and using the cloud to its advantage, right? For the first time in that particular scenario, you actually can change the whole file system out. So the download to that other EBS volume might happen on a smaller instance off to the side. You can get it all ready to go and swap it in milliseconds. It works much faster. Yeah.
Next.
Okay.
You have to skip Kafka.
Yeah, Kafka. Okay. We use Kafka as our main pipeline delivery system, right? Given how much traffic we use, we're fairly conservative with this, so we haven't moved up to Kafka 9 yet. But this is a great lesson from a scaling perspective, right? My message to everyone is don't design your software around your hardware, right? Or configure your software based around your hardware. So originally the pipeline was designed to run on a bunch of Dell servers that had capacity for a massive number of disk drives in them, right? Which resulted in brokers that had large amounts of data, 17, 18, 20 terabytes worth of data on one Kafka broker, right? That sounds great. You can pack them in. You can get a lot of stuff through the rack, in and out. The only problem is when one of them dies, you're now replicating and trying to fix 20 terabytes worth of data, right? So it turns out that just because you have the hardware to do something at scale doesn't necessarily make it the best way to do it. It's actually turned out better for us to start building them as smaller, more dynamic brokers, many more of them, smaller amount of drive. If you lose something, you lose a much smaller percentage. Replication and rebalancing actually turns out to be much better. So just a quick lesson learned from us on that one. Again, we're going up to 0.9, right? It's much more efficient we haven't tried Kafka streaming or anything else like that yet. We use the Mirror Maker. Requires a lot of tuning and experimentation from our perspective, right? Uses a lot of memory, but it does work, right? But it does. Our advice to you is definitely be in a tuning form with that and be ready to play with that. We've moved now to using the mirrors within Docker containers And I'll talk a little bit more about how we run Docker in our organization, but that gives us the ability to they're stateless, so it gives us the ability to fire them up and go quickly. You want to talk about Cassandra, or do you want me to? Okay, I'll go ahead. So just some lessons learned with scaling Cassandra as well. We run this for a number of different things. We run it for some time series database, which I'll talk about near the end. And we also use it as a key store and a user store. Cross data center replication, in our experience, needs a very, very solid network and very focused deployment, right? Repairing across worldwide data center replications can be quite challenging. We've actually moved away from that. We've actually moved to a much more eventual consistency type model, just based on how we're growing as a company and some of the places we're having a network, it just didn't work for us. Again, as Frank said, this is a real key thing here. Optimize your data model to avoid deletes. If you can find a natural way for Cassandra to delete your data, do that. It's much better, and it compacts a lot better with the different compaction strategies than physically deleting data. It works wonderfully for time series data because of that, right? If you can use the time series and the TTLs to naturally reduce your data, you'll win a lot. Again, removing an unnecessary cleanup, just try not to do that in Cassandra. Key value mapping, if the key and the value are very similar size, right? It's very inefficient, needs specific tuning. We found Voldemort works better in situations like that. And the number one thing for our learning is no matter what SSD you get to put in Cassandra, make sure the trim works. Make sure your controller card works. Do some bench testing on your hardware before you try to do this at scale. So we use, and we've moved to Mesos Marathon for our microservices architecture in our points of distribution and our outside data centers for our bidders, ad servers. So we run Docker with Mesos Marathon. We find that works really well for us. Mesos is really good at finding just that little extra spot to put just that extra little Docker container. Compared to running VMs and having to shrink or expand or try to find the optimum VM layout within a data center, right? Mesos provides us a lot more flexibility scaling across a lot of heterogeneous equipment. As Frank said, right, you very often find over time that you've built up one machine in a rack that has 24 cores, another rack has 32, right? Mesos is great for finding ways to fit everything in there. It's also allowed us to do some other experimentations. For example, instead of having a heterogeneous bank of 200, 300, 400 bidders talking to every ad provider out there, we can actually make groupings now and have a set of Docker containers scaled for Google and another set of Docker containers scaled for LiveRail and another scaled for a different provider. And with Marathon, it's very, very easy for us to just say, hey, we're getting pounded by Google this week for this campaign. Just make this bigger. Right? And we can actually shut off the ones that aren't. We still don't do that automatically. We still do that with human control, but it provides tremendous flexibility. There's some hints, too, about using Docker here in this kind of environment, right? Never try to do when you're in a big, 300, 400, 500 containers, even 100 containers. Don't do them all at once. When you have an orchestration mechanism, whether it's Swarm, whether it's Mesos, do 10%, do 20%, do 30%. Give the poor Docker registry a chance to recover from everybody hitting it all at once, right? You'll find much more smoother deployments, and it gives you a great opportunity to do canary deployments as well. Do 10%, double check it. If it's good, do another 10, do another 10, do another 10. Clean up, make sure you get rid of your old instances, right? Make sure you get rid of old instance data. Make sure you've got a logging strategy that works, right? Where are your logs? Are you going to use syslog? Are you not going to use syslog? Just don't let your instance, your Docker container hosts fill up with log files. It's a common mistake, and we've had that happen to us in the past. Minimize your Docker images. You guys have all heard this, right? Make them as small as possible, but don't leave off some of the core tools in our experience. This is our opinion, right? If you need to be able to make yum or apt-get in your Docker container, be able to go and get that one tool you need right now in that one container in production for debugging, allow yourself to do that. Lots of people say you're not going to debug in production, and the reality is sometimes you are. So allow yourself the ability to do that. Just makes your life a lot easier at 2 in the morning. And let's talk a little bit about our move to the cloud. So right now, we started this off as a 500 node cluster in a fixed data center, right? And you have some beautiful advantages when you do that, right? You have a networking team that builds you a 160 gigabit spline that absolutely positively screams, and the data works beautifully and everything works. But you have 500 nodes, and the day that you need 600 nodes, you aren't going to have them, right? And so everybody stacks up and things stack up. So you don't have the elasticity. So you move to the cloud, okay? And that sounds great, and everything's wonderful, and it's going to be elastic. But there's gotchas there, too. You've lost that 160 gig spline, right? You've lost that network team that you can call in the middle of the night to find out why you're having trouble. You've lost sometimes the capacity to scale. The number of instances you think you have aren't always there. Also, object store versus HDFS. They're two different animals. Be very careful as you start using object stores. You're going to want to make sure that you don't go back and forth. If you have multiple jobs and you're going to read from S3 and process, do local HDFS for your temporary data, right? S3, Google Object Store, they all take a lot longer than local file to write. So you'll slow yourself down. Grab your data, do all your processing. At the end of an extended workflow, write it back out. And we right now are leveraging Qball for scalable Hadoop and Spark. So that's an interesting product to check out. Qball actually orchestrates EC2 instances or Google Cloud or Azure instances to make a cluster, manages automatic scaling up and down and using spot instances, et cetera. It's an interesting product. We're just starting to use that. And then lastly, talk real quick about how we're scaling our time series data. So as you imagine, as we start building more data centers and we start scaling out, we've gotten to the point where, as much as we like to monitor, right, writing 1.2 to 1.5 million metrics per minute into Graphite, we've run out of ways to scale Carbon and Whisper and make that all work. So we've come up with some interesting ideas. We've kind of done a little homegrown experiment. We spent a lot of time looking at what was in the environment, in the open source environment, especially with Cassandra and HBase in terms of time series. So we basically made a very simple time series database out of Cassandra. It works beautifully for it, right? Wide tables, everybody's doing it. We did a couple of interesting things we thought we'd mention. We used the Strat.io Lucene plugin in Cassandra, and we actually take our metric names and our metric tags and we put them in a second table, and we use Lucene to scan that table and index that table. So if you want to do a wildcard of a bunch of metrics like you would in Graphite, right? You can find those metric names and get that list and then use that to extract your time series rows separately. We use Spark as our custom query engine against this. It's worked out really, really well. Spark and Cassandra work very, very well together. So we actually have a custom Scala-based query engine that goes in through Spark, extracts data out through Cassandra, and is able to process it, do the necessary math and all the necessary functions to that data, and present one array back to a Java microservice that actually mocks the Graphite API. So basically what we've done is if you want to use Graphite or Grafana, you go to that mock service, it goes to Spark, it does the queries, and it reads out through Cassandra. Our next experiment that we're starting to do now is how do we start doing anomaly detection and curve detection, right? So looking at, if you've got everything's writing fine and your ad servers are fine and all of a sudden something drops off, we're still at the point now where we've got humans watching some of that. Our next experiment is how do we get Spark to start watching that, right? And start telling us when the differentials are tanking or something's going wrong with curves, et cetera. But it's an exciting project that we're doing, and we think that scales really well. We've been able to do it for a much lower cost in Amazon than trying to run Graphite. So we suggest that, to people, if you're looking for a way to scale your time series, definitely look at Cassandra. There's lots of tools out there for that. And that's pretty much what we have for you. Any questions? Okay.
So I have a question.
Okay.
Well, these amount of data is it in your process? I saw it in IoT systems, but what do you process with it?
So we have we'll take in 80 billion bid requests a day, right, for advertising bidding from different open RTB providers, right? And so we've got to go through those at the bid edge and decide what we're bidding on, what we're not bidding on, based on users that we find in our system, based on a number of other criteria, and then basically either accept or reject those bids, make a bid or not make a bid, right? And then what our system has to do is then also take that data and bring it back. So it's obviously important to us what ads we've sold, what bids we've made, what we haven't bid on and why, right? Because that also tells us interesting information about what's in the ad ecosphere right now and what users are coming in and what they're looking at and what people are doing on the web. So we also process all of that data that we don't bid on. So we take some of that as sample data, right? And some of that is actual data into the system and bring that all back and then process all of that.
Prediction thing is the next you do with it, and or is it integrated in your system already?
So
Go ahead.
it's working.
Yeah.
The prediction stuff, what he was talking about is basically the stuff for the monitoring and for the calculation numbers. Our system based, we have an internal DMP, data management platform, where we also collecting information about user behavior in a similar way as you had heard from BOL before in the other talk. And we combine this with the data, what we get out of our bid requests and impression requests, and build out of them the models for future bidding for certain users or for general strategies. And there's also a lot of machine learning in it, which feeds then back. And to give you some numbers, we are right now writing approximately 17 terabytes a day to S3 from worldwide to one data center. So, and there's a couple of challenges in this if you want to scale S3 to that things.
So any questions? More? No? Then, thanks a lot.
Thank you.
Thank you.